Thanks, fun to be here. And if any of you want to see my F-150, it is outside. You have to wash your hands before you touch it. So, like I said, my name's Derrick. I love this security talk. I'm actually not like a security expert. I don't know cryptography. I know it from an end user perspective. So like Mike said, my background is systems. So distributed systems, that's what I love. You know, everything from REST and all those fun buzzwords to distributed databases, peer-to-peer applications, all that fun stuff. So that's what I want to talk about is from an end user perspective, how do we use these cryptographic primitives? What are the different cryptographic goals? And really the end goal is, I feel like my area, my knowledge and security is mostly, I know where my limits are. I know what I don't know, and I know when I need to think deeper and go look it up. And that's actually where the title of my talk comes from. So how many of you have ever gone into a code review and said something like this? So, hey Joe, here's my code, here's my change. You know, here's some loop. And the reason I'm doing this loop is because I saw it done over here. Anyone ever said anything like that? No? A few hands. I think most of you are lying. I actually do it all the time. And I don't think there's anything really wrong with it, right? There's a successful pattern. This is how they posted some message to Twitter over here. Or this is how we integrate with Facebook. Nothing wrong with that, right? But it actually becomes a problem sometimes when we don't really understand what we're doing. Sometimes it's just unnecessary. Maybe we include extra patterns in our code. Or maybe we just simply obscure it a little bit. Where security is, maybe it's a little bit more problematic. Maybe we really haven't secured our application. So cargo cults, has anyone heard of cargo cults first of all? Yeah, kind of fun. It's a little fun term that people have popularized to become a metaphor. So it actually comes from science of anthropology, really famous for after World War II. There was this funny situation where these modern military powers came into contact with these primitive societies, particularly in the South Pacific, brought in planes, built airfields, and they started to, people in these native islands started to get all the benefits of these industrialized civilizations, jeeps, planes, canned foods, weapons, all this really cool stuff. And then suddenly, in 1945, they pull out. And anthropologists observed that afterward, these societies started to do stuff like this. Started to build bamboo airplanes. And you see in the background, it's kind of hard to tell, in the background right there, there's actually a bamboo radio tower. People were sitting there with wooden headphones carved out. What do they want? They wanted that cargo. And so anthropologists called them cargo cults. And it's actually been observed many times. And what they found is this ritualistic practice. They were imitating what they've seen other people do. You know, nothing wrong with building airplanes, and yeah, it helps, but it just didn't help them with their task at hand. They probably needed to learn, you know, how to manufacturing rather than this, you know, these bamboo transportation vehicles. So Richard Feynman, Nobel Prize physicist, popularized the metaphorical use of the term cargo cults. He talks about cargo cult science. You know, it's the imitation of performing experiments and scientific methods without real scientific integrity. And then, you know, of course, our soft science, computer scientists took the term and called it cargo cult programming. It's the ritualistic inclusion of code or patterns that are unnecessary for the task at hand. And so I'll give you some of my own little, these are totally me, design patterns. We always create factories, right? Why do you create factories? Because it's what you do, you create factories. Why do we have wrappers? Well, I may not want to use this library in the future, but I'm going to swap it out for another one, so I wrap it, and then I wrap that, and suddenly we have Java logging. And another one of mine, one little pet peeves, dependency injection. I use it, it's useful. Sometimes it's not necessary. We often overuse it. Any other pet peeves, anyone else? Think of, you know, what's an overused pattern? Something they've seen in their work, something they've done, design pattern, yeah. Escaping stuff? Yes. Yes. Like double HTML encoding it or something like that, or URL encoding it. Yes, thank you. Any other things you've seen people overused? Come on, pet peeves. We all have them, right? Anyone else? Okay, I'll get mine then. Last one is cryptography. So you want a secure application, right? We're building these web applications. They're on the internet. Attackers have access to them. So we had encryption. No, that is not the solution. Encryption is one tool. It's one of many tools. So So most of the examples I'm going to walk through today are actually examples I've seen in code bases I've worked on. So we're going to walk through a bunch of anti-patterns. The goal is to simply get us to think more deeply about security. I do want to give you some tools. I actually want to list out many of the different security goals and differentiate them, as well as some different cryptographic primitives. We won't do an exhaustive explanation of all of them. It's kind of out of the scope of this, but I do want to give you some tools to think about and hopefully give you some direction so that when you do need to, you know where to look and what to think about. You know what questions to ask yourself. So, big picture. This is your big picture when you're securing your web applications. You have some code running on one node. You're sending messages to another node. It's a distributed application website, right? And the attacker owns the network. They can change messages. They can delete messages. They can duplicate messages. They can fabricate their own messages. They can do anything they want. This is the network. It's the only way we're going to be able to securely communicate is to use a variety of approaches. So here's a table. I actually took this from a talk by some VeriSign computer scientists. And actually would point you to them if you want to find out more. It's a great talk. It's actually given at Java 1. It's not specific to Java at all. They actually fill out this table very methodically. We won't do that. We'll focus on kind of the opposite, the inverted table, what not to do, and with a few samples. I do have a link to their presentation at the end, so if you want to see more methodical analysis of all these different tools, it's really good. But let's look at, this is the encryption I mentioned about. This is what, is kind of most people's go-to moves. Symmetric key cryptography. AES encryption, blowfish encryption, we're going to encrypt some stuff, it's going to be secure, it's going to be secret, and that is a valid and recommended approach. There's a whole bunch of other primitives. We have hashing, we have hash-based and just plain old message authentication protocols, asymmetric key cryptography, public key cryptography, digital signatures, and digital certificates. And they map to various goals. We have data integrity, like did someone mess with my message, change it, alter it, authentication, who sent it, non-repudiation. We can actually guarantee that someone cannot deny that they generated some message or performed some action. Confidentiality, it's kind of a very common one, right? Is it secret? Is it safe? And trust. Do we trust this public key, for example? Is this really the public key for Google.com? So first, anti-pattern. We walked through a bunch of fun patterns. I had a lot of fun looking at this. And I actually have all this code on GitHub. Links on the first slide, and it's on the very end too. So you can go try it out. It's just for some very simple PHP code. You can try it, run it on your own little website, and try out this code yourself. So, how many of you have ever worked with signed URLs? Some kind of secret or secure URL. For example, have you ever wanted to put an image in some public place like S3, but you want to be able to hand a URL to it and have only a certain authorized people access the URL. Pretty common. Google Docs does it, right? Has anyone ever used that with Google Docs? You can set the sharing level to only people with this link can see it. So let's try to do that ourselves, try to implement that. So, like we say, we're going to go with this is something, we have a secret image, so we're going to encrypt our ID to it. I've got my plain text image, let's just say there are a bunch of integers. So I got image number 100,000, I got some list of images. This is my private image that I'm supposed to have access to. So the website's going to create the signed URL, a secured URL for this plain text ID. So we're going to encrypt it, blowfish encryption. I've got a secret key and some other stuff here. And here's my plain text ID I'm encrypting. And it turns into some ciphertext. So I append that to a URL as a query parameter, secure ID. I've got this link to a secure URL. So that code actually generates that URL right there. I'm going to give a little disclaimer. I ran this on my laptop and I don't have a certificate. So the HTTP versus HTTPS is actually not any of my examples today. It might be a little distracting. So when I kind of give anti-patterns, we should all be over HTTPS, but my laptop wasn't. So this is what we're looking at, secure ID. The other side, let's see how we actually serve this secure URL. We've got this private image.php secure ID equals and some gobbledygook. Run through the code, we read out that query parameter, we decrypt it, great, that's what we want, right? ID 100,000. And we're going to read out the image and serve it back to the user. And it's, you know, some team photos, actually a team photo we took on our roof this last summer. So let's see how we can attack it. Attacker controls a network. They don't have to control a network in this case. All they have to do is be able to get their own URL. Let's see if I'm malicious. That's my URL. What if I flip the last bit in the URL? Change an E to an F. Let's see what happens. My code's going to my secure server. Service is going to get that query parameter, decrypt to 100,001. Flipping the bit in the ciphertext actually predictably can flip bits inside of the plain text. So suddenly I've got Napoleon's secret plans for the Battle of Waterloo. And I'm served out to someone who wasn't supposed to get it. But we can go on flipping bits all day long, get all the secret images we want. So clearly we failed, right? Let's go on one more example. So I'm going to fill out kind of the inverted table here. Symmetric key cryptography does not give you data authentication. Don't try it, you will fail. Another one, let's take a banking application. Very similar. It's my birthday. I got $150 in cash, $150.01, because my 4-year-old gave me a penny. And I'm going to deposit it. So, you know, some teller terminal probably. And they're going to have to send a message to the bank central server saying, you know, credit my account $150. And of course, you know, there's some authentication going on here, so we're actually not going to focus on that. But, you know, there's some teller. Sam has some authentication tokens going to send along with it. And the terminal is going to encrypt it, send it to the server to credit my account. But, well, here's the code. Here's the terminal. Here we're using AES encryption, CBC mode, industry recommended way to encrypt data. But the attacker controls the network, and this is one line of code he has to run to modify the message. He's taking the 45th byte of the ciphertext, and he's XORing a couple values. It's taking the ASCII value for period, ASCII value for 0, and he's mucking with the message. Terminal, the server is going to decrypt that message. How much money do I get in my account now? That's a nice little birthday present to me. And yeah, you know, my message, my little note from my deposit got screwed up a little bit, but I don't care. I got my money, plus a little buck extra. So, symmetric key cryptography does not give you data integrity either. What does it give you? Confidentiality, and that's it. It's useful for confidentiality. It doesn't give you integrity. So let's go back to our secret image example and correct it. How can we correct that? How can we effectively sign and create a secret URL? HMACs, hash-based message authentication codes. There's other ways to do it. This is just one way. My go-to move, I probably do some cargo cult security programming because I love HMACs. They're really useful. And they're really simple. So this is the code to generate the URL. We have my plaintext ID. I'm going to create a hash of it, but an HMAC it's a series of hashes, and it takes a secret key as part of the input to those hashes. A hash HMAC is just built into PHP. It's in every language, .NET, Java. It's an industry standard. There's an RFC for it. You can go look it up. Don't implement your own. Just use libraries, though. But you see, it takes an algorithm. I'm using SHA-256. This is HMAC SHA-256. My secret key and my plaintext ID. I'm actually going to pass the plaintext ID in the image. My ID really isn't secret, right? The image is. So who cares if it's 100,000? That's probably public information, easily guessable. It's just some auto-incrementing ID. I'm going to put that in the URL. And I'm also going to put this other parameter, which is a digital signature of my URL, which is just this long text. Some of it even goes off the screen. So there's two query parameters now. The other side, all it has to do, you don't have to know all this code. What it's going to do is it's going to get those two parameters. It's going to regenerate the HMAC, and it's just going to check and see if they match. If the two HMAC matches my own calculated signature, then I'll go ahead and give them the image. Otherwise, tell them permission denied. You know, you're trying to get image 100,001 when this signature is signed for image 100,000. And because the HMAC is created with a secret key, an attacker who doesn't have the key cannot generate that hash. It's computationally intractable to generate another hash that matches it. So much more secure way. So HMACs, they do give us integrity and authentication. That's what we should be doing if we're trying to authenticate, create some integrity, access controls. That's your go-to tool, or one of them. It's a very simple one. You see just a few lines of code. Very simple. I want to go into, we talked about encryption, so let's talk about that a little bit. There's some fun little anti-patterns and wrong ways. Even if encryption is the correct primitive to use, symmetric key encryption here, there's still some ways you can mess it up. And my goal isn't necessarily to teach you everything, the way to do it. My goal is to get you to really look at it, because these examples are in code bases I've used and they're just wrong. So there's generally 5 parameters to an encryption method. So this creates some ciphertext. So we take some plain text and create ciphertext. There's the cipher, AES or blowfish. There's my secret key. We all know what that is. The data you're going to encrypt. And then there's the mode, CBC, ECB, OFB. We'll talk about these a little bit. And then there's an initialization vector. Let's walk through each of these and how not to set those values. And generally what I've seen people do is, well, I'm going to put something in there as long as it decrypts, then I'm going to use it. So the problem is if you do it wrong, we'll see what happens. So here we're using blowfish again, ECB mode. This is electronic codebook mode. Block ciphers, there's a couple different kinds of ciphers. Block ciphers, stream ciphers. Block ciphers, that kind of standard one, AES. Blowfish, AES is probably, the way people, is kind of the recommended way to encrypt something, a recommended way. It's going to take fixed size blocks of your input text or input data and encrypt those in set blocks. So kind of sit here, we're going to divvy up our plain text into something like 128-bit blocks. We're going to add the key, run the cipher, and we get ciphertext. So electronic codebook mode, super simple. But I encrypted this image. Anyone tell what that says? Hobbit, yeah. Suddenly we know what movie the studios are producing next, right? So why didn't it encrypt it? Well, it did encrypt it, but it encrypted blocks of it at a time, and it did not obscure patterns. The problem is, if we have the same plain text block multiple times, both of those are going to result in the same ciphertext block. So electronic codebook mode is simple, has some nice properties to it, but it doesn't obscure patterns within your picture. So here's the actual original picture that I created this encrypted image from. So here's a better way to do it, is cipher block chaining mode, CBC mode. And we see that when we encrypt a block, we're going to take the output of one block and use that as input to the next. And what that does is going to obscure patterns within the message. So simple way to improve that encryption. And then the next one, do a quick time check. So review this. We saw our CBC mode, ECB mode, OFB mode. Cipher block chaining is a better way to do it than electronic codebook mode. Output feedback mode is another one we actually used earlier in the slides. But what you want to do is, mainly I want to tell you to look it up. But just watch out for this, understand what that parameter is. It's the different mode, how we're chaining the blocks together, and how the cipher is being applied to our plain text. Now we're going to talk about the initialization vector. So this is actually the only example on all the slides. It isn't real. I actually ran out of time, this is what I was doing this morning at 8 a.m. So this ciphertext actually is not actual ciphertext. All the other ones are the actual ciphertext you get by running the code I showed you. But this is something pretty close. So we have two camps here, two military camps. We have an orange camp and a green camp. The orange camp is waiting to be attacked by the green camp. And they're observing the radio messages that are, of course, green is encrypting. And on Monday morning at 8 a.m., they see this message being sent by green amongst themselves. They're radioing to each other this message. And they can't decrypt it, but we're trying, we're orange, trying to figure out when they're going to attack. Tuesday, 8 a.m., same thing. Day goes by, nothing happens. Wednesday, 8 a.m., see the same message. Day goes by, nothing happens. Thursday, 8 a.m., same thing. Friday, we wake up, 8 a.m. Our radio operator tells us we intercepted this message. You're the general, what are you going to do? high alert, right? Something changed. Something's different here. So the problem is that this parameter right here. The initialization vector is what's going to help us avoid patterns across messages. We saw our mode avoids patterns within messages, but because we're actually using the same value every single time, I took this because I actually saw this in some code, all too close to me, but luckily I knew that's probably not what we want. So we're using the same value over and over for our initialization vector. What we should be doing is we should be generating a unique initialization vector for each message, and then we avoid this kind of problem here. We avoid patterns across messages. I'll show you real quick. In the previous slide, you can see the actual where the initialization vector comes in is right here. It goes in the initial block and gets propagated throughout all the other blocks of the ciphertext. So if we have unique initialization vectors, we avoid patterns. And really, the initialization vector is not really secret. You can pass it along in plain text, and so this side knows what value to use, and then you avoid this problem of having the same message over and over again. So modes and IVs, cipher block chaining prevents messages within patterns within messages, IV across messages. Something to be aware of. How do we generate keys and initialization vectors? And this is a place where I'm not an expert, but I do know what not to do. I do know I need to go look it up. And I do know don't do this. So here a key, let's just say this really is some, how I generate it, some random thing. I've got some ASCII text. It's 16 bytes, 128 bits. So that's our goal. We want 128 bits, 128-bit key. Create some random number for our initialization vector. It's correct, what we learned, right? And then we create this is AES encryption. We're going to create some ciphertext. What's really going on here? How many bits of key entropy can be contained in 16 alphanumeric characters? 96 bits. It's ASCII, right? And we're only using alphanumeric characters, so really we're only getting about 6 bits of entropy per byte because we're only using alphanumeric here as input. It only results in, that's 2 to the negative 10. I guess it's 2 to the negative 8% of the possible search space of a true 128-bit key. So we're just missing out on some opportunity to really make our application secure. Again, just something to think about. If you want a 128-bit key, think about the entropy. By entropy, I mean amount of information that the attacker can't guess. So, and what initialization vector is really being used here? I chose RAND, but the problem is the initialization vector has to be at least as big. That should be the same size as your block. And RAND isn't. If we're using a 128-bit block, then we're going to get this value for initialization vector no matter what we put in. The reason is, and luckily PHP warns you, you're going to get this warning. Warning, encrypt, decrypt. Actually, I copied this. Decrypt gives you the same message. Encrypt will give you the same one as decrypt. The IV parameter must be as long as the block size in, here's my file online. So if you don't give it long enough block size, it defaults to all zeros, and you have the same problem you had initially. So simply watch out, make sure you're using long enough initialization vector. Just, understand the principle, think about what you're doing, and make sure, look it up really, and make sure you're doing it correctly. Here's a correct way to create an initialization vector. Again, don't write the code yourself. Just use some really great tools built into PHP. You can even ask. You don't even have to know what size of initialization vector you need. I actually have a mistake in my code here. I think that is correct, but 16 bytes, 128 bits. But really, we should get the value from here. You can go ask, okay, I'm going to use this cipher in this mode. Tell me how big my IV needs to be. And actually should be using that value inside of encrypt create IV. It'll do it for you. You don't have to think about it, and you don't have to worry about whether or not it's correct. One more anti-pattern, random values. Oh, I've seen all these in my code, in code bases I've worked on. Cross-site request forgery. I'm not going to dive into it. Assume you know a little bit. I'll give you just a brief background in case this is a little bit new idea. Cross-site request forgery. Problem is, browsers are going to send my cookies along to whatever server the request is going to. So evil.org can create some form and perhaps trick me to click on submit button on the form, that doesn't go to evil.org, but it's going to go to lucidchart.com. It's going to, some other location where I've got some bank account information, and it's going to cause me to donate some money. This is the accurate form. It's a real form that exists on a legitimate website, but evil.org is going to reproduce it and trick me into clicking on it, and it's not going to go to evil.org. It's going to go to some other place where I've got some credentials, I've got a cookie, it's going to be sent, and it's going to cause some malicious action to be taken on some other server that evil.org is interested in. So we prevent this attack. This is the recommended way. A recommended way to prevent it is simply by putting some kind of random value, not in a cookie. In addition to some cookie, we also going to put it inside of our form or inside of the data that is submitted or posted to our website. So I'm trying to do that here, creating a random value, sticking it inside of a hidden input field. And this is my form. So when I go and click submit, my server can go and verify that the form has the value that happens to match the cookie, and that I know that I generated this form. Problem is our random is pseudo-random, right? And most default random number generators in PHP or Java are linear congruential pseudo, I don't even know if I'm pronouncing that right, but pseudo-random number generators, LCG, you'll see the acronym. And even if they're not this, even if they're a little better, Mercy Twist, other ones, there's still a fundamental problem with it. There's not a lot of entropy inside of it, and given a couple of values, you can actually calculate the internal seed of the remote server that's generating this random value and therefore predict every subsequent value. So all the attacker has to do is go to my site, get the form twice in a row, run this little bit of code. This is Java code, sorry. And suddenly they can go calculate the correct form with the correct XSRF token. I'm going to go on one more. Before we show the correct pattern, I'm going to show another anti-pattern with pseudo-random numbers, session IDs, something else I saw, and some white hat hacking before anyone believed me it was insecure. I'm going to create a session ID in my site, right? I'm going to create some random value, serve it, and set it in a cookie so I can go and authenticate the user in every request. As input, you can say, based on this last example, you can say, okay, well, Derrick, I'm not that dumb. I'm going to hash it, right? I'm not going to go send a random value. I'm going to hash it. So, okay, well, let's try that. I'm going to create a hash, and I'm going to add some extra values to this input as well. I'm going to add the user ID, random number, as well as a micro timestamp. We're getting lots of bits of precision here. User probably can't know exactly down to the microsecond what timestamp my server has, and I'm going to send that as my should be session ID. So how secure is this now? Well, we haven't really changed the underlying entropy just by hashing it. Not only that, but adding extra parameters. This is probably not secret. User IDs generally are not secret, right? They probably exist somewhere, even if they're not in the UI. They might be in the JavaScript or URL or something. I could probably know user IDs and even guess them that they're probably auto-incrementing or UIDs or something. Microtime, I know what time it is. I'm an attacker. And even if I don't know exact timestamp, there are actually algorithms out there that can help an attacker get down to within about 11 bits. 11, I actually put, even gave ourselves a little conservative estimates about within about 15 bits of precision of these remote server's timestamp. So RAND, people have estimated there's only about 5 bits of precision inside of some basic old RAND, 15 bits of precision here. So we've got 20 bits of entropy inside of here, and even though we're hashing it, the GPU can calculate that in under a second. Can calculate that many 2 to the 20th hashes in a second. We say, okay, well, Derrick, MD5, I know it's not the best. We shot 1, okay, we got up to a minute. We shot 256, get up to 10 minutes. Okay, hacker can attack my site in 10 minutes. So we can always add more band-aids to this is usually what to get people going on. Okay, well, I'm going to add a process ID. Well, I'm going to add this. There's a better way to do it, much simpler, more secure, and HMAX and secure random. First of all, secure random, OpenSSL random pseudo bytes. Super simple. You tell it how many bytes you want, 32 bytes, and suddenly I've got a 256 bits of much more secure random number. Tons of entropy, really hard for an attacker to guess. I don't have to hash it. You can hash it if you want. I don't care. But go ahead and stick that in our XSRF token, and then we'll use that to prevent cross-site request forgery attacks. And for the other one, another pet peeve of mine, don't use sessions. I have no use for sessions. Use HMAX. You can use HMAX, you saw those earlier. Why in the world do you have to do a database write every time I log in? Why in every single request do you have to load in suck in a ton of session state from database? Assuming you've got a multi-node system. HMAX, you don't have to do a database write when I log in. HMAX, you don't have to do a database read. It has nothing to do with security, but it really bothers me every time I go to a new company and they're using session IDs. Now I switch them over to HMAX. So they're just much more performant, more secure, harder to screw up. So that's the correct way to do. So we've seen that this is how we would correct both our CSRF and our session token problems. OpenSSL. And again, a lot of these, we're seeing they're built into the language, super simple, a little bit of research, just to understand some of the basic primitives and basic properties of the cryptographic primitive, and you've got yourself a secure application. So finally, kind of in summary, no cargo cult security, and this is kind of the takeaway I was hoping to share, is one, identify your true security goal. We saw with the image, well, it's secret image, right? So secrecy, confidentiality, we go to encryption. Well, it's not really what we're going for. We're going for maybe integrity or authentication, since what we're encrypting is a piece of the URL. The URL is, that data we're encrypting is not secret. So think about, identify your true goal, find the correct crypto primitive. I'll actually show you the final filled out table of mapping goals to primitives. Spend some time to learn about it. Look at all the parameters, make sure you're really setting them correctly. There's probably some simple examples out there. Spend an hour or two, and then write as little of your own code as possible. That's kind of my caveat at the beginning. I'm not a cryptographic expert. I couldn't tell you why we use prime numbers for different cryptographic keys. I do know I'm just going to write as little code of my own as possible. I'm going to use one of the 12 people in the world who are capable of writing the cryptographic code. I'm just going to use theirs. And then probably pretty safe. So here's the true mapped out table. We mostly covered some of these ones. And I think this is mostly what you need. I mean, asymmetric key encryption, you can simply buy a certificate. You're going to set up HTTPS on your website. You don't have to write a whole lot of your own, so I didn't cover a lot of that. Digital signatures, RSA, stuff like that. Definitely get an expert if you're doing any of that. But some of this basic stuff, if you just understand some basic principles, I think use someone else's code. There's a lot of great things you can do. A lot of it's built into their frameworks. Effective ways to do it. Or really, as I like to put it, don't you dare do any of this. If you do this, you're a nincompoop, and I'm going to come and change your code. So my name is Derrick Isaacson. I do have the last slide here you can go look at, including if you want to see all the samples and my actual code. I've got, I don't think I have it on here. I guess I have it on the first page, the link to the GitHub URL if you want to see all this code and try it out yourself and muck with it and encrypt your own images. What questions do you have? Yeah.
Your last correct kind of do anything to expire something as far as preventing replay tax?
That's a really good question. So your question is, do we do anything to expire CSRF tokens to prevent replay attacks? Well, one, we should always transmit them over SSL, right? If we transmit them over SSL, we set a cookie, something user-specific about it. We don't have to set a cookie. You can store it in the server. If you are doing sessions, you can store it with the server. Anyway, what I'm getting at, you send it over SSL, so no one but your intended user can access it. It is user-specific, so I guess I'm thinking out loud here. I'm not seeing a replay vulnerability unless I missed something, because the user it's intended for has it and no one else has it. I guess you're talking about, probably going back to my own words, about how the attacker can replay messages. But if the user didn't, I guess if they replayed in some entire HTTPS request, is that what you're getting at, to do some post?
Well, the general assumption that I can't post it.
Yes, no, that's a good question. I'm thinking out loud. Yeah, that is probably a good question. I actually don't know. I haven't seen, I looked at the OAuth recommendation, and I didn't see anything about any recommendation that needed to be expired. They actually even recommend just fine to use them across an entire session for a user, reuse it across forms. So that is the OAuth recommendation. So yeah, I'm not aware of a vulnerability, but it's a good question. Yes, yeah. So yeah, and say OAuth, you can go look at the OAuth one, and they do talk about the vulnerabilities of reusing it, but they even say it's acceptable to reuse them across a session because it is user specific. An attacker doesn't have access to it. The only person who can replay it is the user, assuming you're sending over SSL. So, yeah.
I'm curious on that HMAC versus session.
Yeah.
I feel like everything else, at least I have enough that I can go look it up.
My rant about why you shouldn't use session IDs, you mean?
Yeah.
Yeah. A lot of it, two problems with session IDs that I've seen. One of them, people just do them wrong, like my anti-pattern there. That's real code I've seen before in code base and doesn't exist anymore because I went through and said, here's how I hack it. The other problem is less of a security problem, more of a performance and scalability. Like I said, my personal real passion is around systems, distributed systems. So HMACs, and I really glossed over it. The HMAC example in here is from the images. Really, it's the same principle, but instead of creating a digital signature for an image ID, go back to that and replace that with a user ID. So your cookie, your authentication cookie, is a digital signature of a user ID. What that allows you to do, the code is here. I guess we can go back to it. It allows the endpoint that performs the authentication to not do any database lookup. All it has to do is regenerate the hash, see if it matches the one given to it, and it will only authenticate the user if the two values match. So let's see if we can go all the way back there. Here we go. So here's the code. So your HMAC for authentication is going to be, you're going to, instead of a query parameter, you read some cookie probably. And the cookie is going to have an HMAC and a user ID. The code is going to read both parts. It's going to recalculate the HMAC based on its private key. And if the two match, then you authenticate, I know I'm their user 245. Does that help?
So rather than having to get a user ID to check the database?
Yeah, you don't even have, that user ID is authenticated at that point. The only person who generated this authentication token is your server. Now, you can obviously, if you really want to go look up, see, well, do they have a license or something, you can go look it up. But that user ID is authenticated at that point without doing any requests outside your system. No, we didn't have to make any requests in a database or service or anything. Just authenticate that they are user 245. Yeah, thank you. If it's all right, I'm just going to repeat it for the purpose of the video. So I think the comment, very helpful. He pointed out that AWS creates signed URLs with HMACs, right? Am I saying that right? Yes. And actually, similarly, if you want examples to go look it up, I've done this on other slides too. I didn't put it here because this is a PHP conference. But for Amazon Web Services, they use HMACs as part of the authentication if you're an AWS customer. You're trying to interact with the AWS APIs to launch a new server or something. They actually use HMACs, and they have sample code on their website. It's written in PHP, but Java samples abound as well. But you can go look at how AWS uses HMACs for authentication in their system, in addition to signed URLs, but just as a header or something like that, another parameter to authenticate a user in a request. So you can go, if you just Google HMAC SHA-1 or something. I can actually use SHA-1, HMAC SHA-1 for AWS. You'll see code samples and how to use it with their API, and you can mimic that. Any other questions? Well, thanks so much for having me here. Again, my name's Derrick. I'd be happy to, I'd be happy to connect with any of you over email or anything. So my email's at the end, and if you have any thoughts on my GitHub project as well, Cargo Cult Security. So thank you very much.